Assalamu alaikum wa rahmatullahi wa barakatuh. This is Islam Mohamed Mahmoud Ismail. Today I will present my final year project. My final year project title is Object Detection of UAV Images using YOLOv3. This project is supervised by PROF Dr. K. First, we will introduce my project. I will go into introduction. Recently, UAVs are getting used widely because of the multifunctionality and portability of UAVs, especially drones. And the individuals need a neural network system that operates with the UAVs to identify objects in real time. Every year, a new deep learning algorithm is released that solves many issues involved. In today's application, the implementation of computer vision methods has been widely used in object detection and classification. So, what is object detection? Object detection is the ability to determine the location of the object in each image, also known as object localization. However, determining which category that this object belongs to is known as object classification. My problem stated here, the current problem with object detection is the processing time taken by the model to detect objects in an image. By using a model with a similar architecture that has fewer convolutions, we arrive at a model that is smaller and requires fewer resources to train, and we can minimize the time taken by the model to detect objects in the image. The project aims to solve the problem statement by achieving these goals. First, to prepare suitable UAV image database for training YOLOv3. To develop object detection of UAV image using YOLOv3, finally to evaluate its performance. So now we should know what is YOLO. YOLO, you only look once. YOLO, you only look once. It's a real-time object detection system. YOLO is an algorithm that uses regression to detect objects. It takes the input image and determine the classification of the object and specify the coordinates of the bounding boxes. As shown here in the figure, YOLO architecture has 24 CNN networks layers, followed by 2 connected layers CNN. Okay. For the CNN layers, it's used to extract the features from the input image, while the remaining connected layers are used to predict the output probabilities and coordinates. Basically, it divides the input image into S grid cells like this figure. And then each grid cell will predict inbound boxes and their confidence score. First step is dataset selection. We choose a suitable dataset. Next, model selection. We're picking the model architecture. Then implementation, we train our model. Last thing is model evaluation. So for our model evaluation, there is some matrices. We have to consider it to evaluate our project. First one, precision. It is the ratio of correctly detected positive cases from all the positive prediction. It is effective when the cost of false positive is high. Second one, recall. It is ratio of the correctly detected positive cases from all actual positive cases. Last one, the mean average precision, MAP. MAP is used to evaluate object recognition algorithm like RCNN and YOLO by comparing the ground truth bounding box to detected box. The MAP drives a score. The model's detection accuracy improves at the score rises. Now we're going to data preparation. So our VIST-drone dataset was pre-processed by converting it into suitable format for the YOLO model. The conversion process can be summarized as following in this flowchart. First, we'll go to extract annotation from original VIST-drone annotation files, convert top left XY, center XY, then read image size according to the annotation file name, then normalize X and height by image height, then normalize Y and width by image. Last thing, save results to new file with the same name under the labels folder. Now for the result and discussion. This is the process for our experiment. We started, then collected data set, then we do a data pre-processing, then we train our model, test the model to detect objects, last thing, analyze the result, and rewrite the report. We have trained a total of 4 different models, 2 with YOLOv3 tiny architecture and 2 more with YOLOv5S architecture. Now we will discuss the results of each of the models. The first one, YOLOv3 tiny without fine-tuning. From this result, we can see that the model is not doing very well. The important metrics, precision, recall, and MAB fall under very poor performance as shown here in the table. From this graph, we can see that object loss increases with time, which means the model is not learning regarding object loss. The 2 other loss functions are decreasing, which indicates that the model is learning to optimize those loss functions. So for both the loss function are decreasing very slowly, so we might have to use a larger learning rate to increase the model step towards the loss functions. Second model is YOLOv3 tiny with fine-tuning. As shown here in the graph, the loss functions for this model are similar to the previous YOLOv3 tiny without fine-tuning. The object loss increased with time, which means the model is not learning regarding object loss. The other functions, box loss and classification loss, decrease slowly. However, we can tell that the model performs better than the last version without fine-tuning. It is appear here that the 5% MAP and 95% MAP are increasing compared to YOLOv3 tiny without fine-tuning, as shown here in this table. 5% MAP increased from 5.84% to 7.78%, and the 95% MAP slightly increased from 2.08% to 2.96%, while recall grows from 8.56% to 10.4%. YOLOv5S without fine-tuning. From this result here, we can see that the model is not performing well from this graph. It also has similar results as before. The loss functions have a similar result for the previous models YOLOv3 tiny without fine-tuning and with fine-tuning. The MAP is going linearly, which means maybe training for more epochs will achieve better MAP. And for recall is going up and going down. It's slightly oscillating. So the learning rate is larger. We have here the last model, YOLOv5S with fine-tuning. As shown here, the loss functions for this model are comparable to the previous YOLOv5S without fine-tuning. The object loss grows with time, indicating that the model is not learning well regarding object loss, or regarding the object loss. The other loss function gradually decline. However, we can determine that the model performs better than the previous version. Furthermore, it's appear here that the 5% MAB and 95% MAB with recall are increasing compared to the YOLOv5S without fine-tuning. As shown here in this table, we have 5% MAP increased from 8.84 to 18.9%, and 95% MAP slightly increased from 3.6 to 9.52%, while recall goes from 13.1 to 21.7%. Here we have our final model, YOLOv5S with fine-tuning for 100 epochs. So the first observation we can make about the graph is the presence of the oscillation in all metrics. This can be due to high learning rate. Therefore, reducing the learning rate might prevent oscillation. Despite the oscillation, this model architecture performs the best compared to others. This can be partially attributed to the model's architecture and the longer training time. Now this is comparison between all 5 different models. As it's shown here, our model YOLO of V5S with 100 epochs is achieved the higher MAP, 5% MAP and 95% MAP. This is some visual results. This is some visual results that our models have achieved. As it's shown here, our system now can classify 12 object classes. For conclusion, the project aimed to prepare a suitable UAV image database for training YOLOv3, develop object detection of UAV image using YOLOv3, and evaluate its performance. Finally, we can say that this project achieved the objective successfully by training of 4 different models, 2 with YOLOv3 tiny architecture and 2 more with the YOLO5S architecture. YOLOv5S with fine-tuning model was selected as a final model for training in this project due to its acceptable accuracy and fast speed in image processing and real-time application. This is all from me. Thank you.